Hello! So let's continue our introduction to elliptic curves. At the end of the lecture today, we'll have defined how to add points together in the elliptic curve group, or at least how to add one point with its inverse. In order to talk about that, I need to bring in some ideas from outside of our math class, and I need to bring in some ideas from art. So normally, we're used to thinking of the Cartesian plane as being flat, and we are looking down from above, usually centered at the origin here. And if we have two different lines in blue and in red that have the same slope, then these lines do not intersect. And that is correct. But there is another way of thinking about this, right? This perspective, looking down from above, is not the way that we actually interact with the world, right? The world is a 3D thing, and we can only see so much of it at a time. And artists sat down to figure out, well, how can I represent this globe that I sit on and try to convey depth in my pictures and things like that. So let's take a look at just a photograph, right? Here's a nice road somewhere. And this is a photograph taken in 1-point perspective. All right, so what does that mean? I've got my horizon line way out on the horizon. You can see it here sort of about 1/3 the way down the height of this photograph. And even though we would expect the two opposite sides of a road to be parallel, they seem to be getting closer and closer together as they approach that horizon line. And so there's a single point marked here by where the median strip is ending. And it looks like the median strip is going to end at some point here on the horizon, as well as both the edges of this road are going to join it out there and meet it at that point. So artists would call a point like that the vanishing point. And since this picture only has one of those, this is single point perspective. The point that is out there on the horizon doesn't actually belong to the road. It's an idealized point. Or, I need to be careful with my vocabulary here, you can think of it as imagined, right? Not that it is the square root of a negative number, but that it only exists in our heads as we try to visually process this image. There's not actually a point at the end of this road, right? It's just idealized. We can bring this same idea back to the world of mathematics. In fact, there's an entire theory about how projective geometry would work and what it means for our eyes to be seeing things, right? That is not what this lecture is about, but that exists, and it's some pretty cool mathematical workings that go on for our understanding of vision. But for our purposes today, we need a mathematical way of thinking of this idea. Is there a place where two parallel lines will meet on the horizon? So in terms of geometry, we would call this point a point at infinity. So this is the mathematical version of the vanishing point idea. The point at infinity is not actually on the xy plane. It does not have an x coordinate. It does not have a y coordinate. We only know where it is because that is a place where parallel lines will meet, and so it will be outside of the plane. The point at infinity, just like the vanishing point out on the horizon, it only exists in our heads. It's an idealized point. But keeping this idea in our heads will allow us to look at geometry and algebraic curves in a new perspective, I'll say. Now, here we have the same graph from before. I've got my lines in blue and in red, both with slope 1. They don't meet anywhere inside the xy plane, which goes on infinitely far and in two different directions here. But you can imagine if you weren't looking down on the plane from above, but you were actually standing in between these two lines and looking out to the horizon, you would see a picture pretty similar to the photograph of the road. It would seem like the blue and the red lines are getting closer as you look out towards the horizon. So there will be a point at infinity that I imagine as being outside of the xy plane. I'll never be able to reach it no matter how far I go, but looking out into that distance, it looks as though those two lines are meeting about where my mouse is, I suppose. Now, the point at infinity for these two lines happens to be over here where my mouse is because I'm following their slope. If I had different slopes for these lines, they might not meet at all. So here's a slightly different example. I've increased the slope of my blue line, and now my two different lines are intersecting inside the xy plane. Looks like coordinates -1, -1. And I claim that these two lines, even if you were standing here and looking out in perspective, they would not be meeting at a point at infinity. And part of the way we can remember this is that two different lines can only ever intersect at a single point, right? That's how they work in the xy plane, and that reasoning extends to points at infinity as well. So this red line is going off to some point at infinity in this direction. The blue line is approaching some different point at infinity along a different direction. And just as a bit of convention here, the point at infinity is technically on both sides of the line. We won't have to worry about that too much. It's just a little fact of how geometers have found this a useful tool. Now, this is already a bit to think about in terms of lines, which is why I introduced the idea for just lines, but it applies to other types of curves as well. And in particular, it applies to elliptic curves. So this will be a lot easier to show rather than to just tell you. And like before, you can click on this link to see the graph that I was working with. So here in red is my elliptic curve. And I've got this bulb here. It doesn't look like it's going off to the horizon, so I'm going to ignore it for now. And then I've got this other part that's going off unboundedly. I claim that the tail ends of this curve, where it's continuing to grow out beyond my window frame, are going to meet at some point at infinity. And in particular, it's the point that's at the end of a vertical line. So here is a vertical line I've drawn in green. And it's difficult to imagine the perspective, right? This line is going vertically, and this curve seems to be going out at a different slope. But as we zoom out further and further, the red elliptic curve is becoming more and more vertical, right? If I continue going out, you can see that now at this scale, the red curve is nearly vertical. The green curve has been vertical the entire time. And for that reason, these two curves, the line and the elliptic curve, are going to meet at the point at infinity at the end of the green line, right? And I could have chosen a different vertical line. Maybe I can choose x equals 5,000 because that coordinate is just on the screen for me there. So here, I don't want red. I want, come now. Red it stays. I don't want to dally. So here I have my vertical line. And as I was saying before, the green line here and the vertical red line here are going to meet at a point at infinity. That becomes a little bit more obvious as I zoom out. The elliptic curve is eventually going to pass this line. It'll have to, because I can just pick x coordinate 5,000, figure out what y coordinate that gives me. But nonetheless, all three of these curves will end up joining back together at the point at infinity where any two vertical lines will meet. So it is convenient for us to imagine that point as being infinitely far vertically above the xy plane. So you can start at any point you like, go up infinitely far. That's the point at infinity for the elliptic curve. And that point, can I get back in? Yeah, there's my bulb again. That point at infinity is going to be the same no matter what formula I'm using for the elliptic curve. So I can change this up. I got rid of the bulb now. And I still have this behavior where the elliptic curve is going out and going out. The further out I go, or rather the larger my x-coordinate, you can see that the slope of this curve is becoming more and more vertical. And for the fact that the slope is tending towards a vertical line, it will meet my actual vertical line at the point at infinity. Now, this is a really important idea. It's also a lot to chew on, so you might want to rewatch this video and play around with the graph yourself. I highly encourage playing around with these things. The very nice thing about the point at infinity, well, it makes the geometry nice in certain respects. We'll see this in Tuesday's lecture. For right now, it's going to be nice that any elliptic curves share the same point at infinity. No matter what formula that we've got, y squared equals x cubed plus ax plus b, that elliptic curve will end up meeting the point at infinity that belongs to vertical lines. And it does not matter what formula we have. And that is a fact that we will take advantage of when we define our group operation, which is the second part of this lecture. I'll see you in a bit.